Alright, day 4 here. So today we're going to talk about the geometric connection between a function and a definite integral. We think of derivatives as the slope of the function, so what can we think of integrals as? Well, before we get into all that, let's do a little bit of review / extension on what we've done so far. Remember, if you throw an object upwards, at that instantaneous moment after it is no longer moving upwards and before it starts to fall back down, we know that the instantaneous velocity at that point where the object is at its maximum height is 0. That's going to be important here in a moment, because here we have a situation. The acceleration due to gravity on Earth is negative 32 feet per second squared. You want to throw a Gatorade bottle directly upwards to your friend standing on the roof of a building. You release the bottle at a height of 5 feet above the ground. Hey there, that's telling us that h naught equals 5. The starting height is 5. Our friend catches the bottle right as it reaches its maximum height of 25 feet above the ground. So we know when the object is at its maximum height of 25 feet, the bottle will have a velocity of 0. And so we now need to use this information to come up with a system of equations. So we have our acceleration function, a of t equals negative 32. So if we integrate our acceleration function with respect to time, we will get our velocity function plus that v naught there, don't forget that. So we're integrating negative 32, so we're going to get negative 32t, negative 32t plus v naught, that equals our velocity function v of t. If we integrate our velocity function with respect to time, we will get our height function, h of t, again plus some constant there, which is our initial height. And so we're integrating negative 32t plus v naught, and so we're getting a t squared term. We need to divide by that exponent of 2, so negative 32 divided by 2 is negative 16t squared plus v naught gets a t, and then plus our initial height, and that is our height function, h of t, right there. Well, again, think about what we already know. We know the height is 0, so instead of saying h naught there, I said the height is 0, I'm going to say the initial height is 5, so we know that h naught right there is 5. So now we have these two equations, but where do we go from here? Well, we know it reaches a maximum height of 25. And so, let's say that we get this equation, negative 16t squared plus v naught t plus 5 equals 25. Now, by setting the height equal to 25, that is implying / forcing this to be true, that t represents the time it reaches the maximum height. We don't know what it is, but that's what that t represents. And so if we then set the velocity equation equal to 0, negative 32t plus v naught equals 0, velocity of 0, that then is forcing this time to also be the max height, because the velocity is 0 at its maximum height. So we now have two equations here relating two unknown values, the initial velocity and the time the object reaches its maximum height. So let's solve this system of equations. No need for a matrix here. In fact, it would be not so easy to do with that t squared term right there, with that t there as well. So let's just do some substitution. So look at this equation on the left, add 32t to both sides, and we'll get v naught equals 32t. Now we can take this expression for v naught and we can plug it in to our other equation. And so we get negative 16t squared plus v naught, which is 32t times t, so we get a t squared, plus 5, I'm going to subtract that to the other side to get equals 20 right there. Now, negative 16t squared plus 32t squared, I have like terms there. Negative 16 plus 32 gives me a positive 16t squared equals 20. And so t squared equals 16, sorry, I'm bad at math, equals 20 over 16, which is the same as divide the top and the bottom by 4, 5 over 4. And so if I want t, then I will get t equals the square root of 5 over 2 by taking the square root of that there fraction. So that is approximately 1.118, I believe. But we are not done. That's the time the object reaches its maximum height. But we want to know the starting velocity, the initial velocity. So look, we have our equation for v naught right there. And so we get v naught, our starting velocity, equals 32 root 5 over 2, which becomes 32 divided by 2 is 16 times the square root of 5 is our starting velocity, which is actually V naught actually is 35.777, and our units are feet per second. And there we have it. So then, that was some slight review, slight extension, and actual goal for the day are to understand what a definite integral is and understand the geometric connection between a function and a definite integral. So let's get started. So here's the situation. You ride your bicycle with a constant velocity of 10 feet per second. What I want you to do is sketch a graph that models this velocity function from time t equals 0 to time t equals 5. And so I'm sketching this function right there. V of t equals 10 between 0 and 5, and it's just a constant function, which means it is just that horizontal line right there. Now, let's think about what the corresponding position function would look like. So let's sketch the position function here next to this one. Well, our velocity is 10 feet per second, which literally means each second we will be moving 10 feet farther. So if we start at 0, after 1 second we have moved 10 feet. After 2 seconds we've moved 20. After 3, 30. After 4, 40, and 50. And so we're getting this nice straight linear function right there as our position graph. But think about what we just did. We took the number of seconds and we multiplied it by the velocity. We took the number of seconds, like say for example 1 second. We took 1 second and we multiplied it by that, multiplied it by that velocity right there, 10, and we got 10 for that first point. And to find our point for the second, t equals 2, we did the same exact thing, except this time we were looking at the second, and we found that value, 2 times 10 right there. And if we wanted that fifth point, we would look at that value right there, 5 times 10. So if you've noticed what's happening here is when we're calculating that position function, we're actually finding that area underneath of the velocity function. Each area there was corresponding to a point on that position graph, which kind of makes sense for a couple different reasons. If you think about it, and you think about the units here, we're taking feet per second, and we're multiplying it by seconds to get feet, our position graph right there, units being feet. And another reason that should kind of super make sense is that we were integrating a constant function. We're integrating the function 10, which means we integrate 10 with respect to time. You should end up with 10t plus some constant, which in this case was 0. But we got this linear function, 10t, linear function going through the origin with a slope of 10. So that's kind of crazy and kind of interesting. So another little area for a connection real quick is if you think about derivatives. If we took the derivative of this position function, we would end up with that velocity function. And so if you think about that process, remember the derivative is the slope of the function. So to find the slope of this line, you would be saying rise over run, y over x, which is a process of division. So derivatives are kind of like dividing, and integration is kind of like multiplying. We multiplied to find that area underneath. So again, the process of differentiating or taking a derivative, you're really just dividing, and the process of integrating, finding an antiderivative, you're really just multiplying. So don't let it get any harder than that. Well, okay. So if you have nothing but a velocity graph for a function, you could figure out those points by finding the area underneath the curve. All right, well, let's look at this situation here now. Same idea, except now we're starting from a stopped position, and we're told that we're increasing our velocity by 2 feet per second each second, which means we're actually given this acceleration function a of t equals 2. That's what increasing by 2 feet per second each second is really telling us there. And furthermore, we know that v naught is 0 because we're starting from a stopped position. And so we want to sketch this, so we need to integrate the function a of t to get our v of t function, which is just going to be 2t, and plus nothing because we're starting from a stopped position. The initial velocity is 0. So if we then integrate again to get our position function, p of t, we're going to get t squared. And so then if we start that at the origin to say the starting position of 0, we just get this simple function t squared. So let's think of this one step at a time now. Let's first graph that acceleration function. So over here, if I have a of t, I know the acceleration is a constant 2. So 1, 2, 3, 4, 5 right there. Here is my acceleration function going over like that. Now let's take this and let's sketch the velocity function after this. So velocity, again, 0, 1, 2, 3, 4, 5. Velocity is the function 2t. So every single x value, you get 2 in the y value, a slope of 2 right there. And so we're going to get this point, let's say 2, 4, 4, 6, 8, and 10. Y value of 1, we're going to get, I'm sorry, x value of 1, we're going to get a y value of 2. Y value of, I can't talk, x value of 2, we get a y value of 4. 3 is going to go to 6. And 4 is going to go to 8. And 5 is going to go to 10. And so we're getting this linear function now as our velocity. And again, we have time on the bottom right there. But again, think about how we could have gotten that velocity function without actually knowing the equation. If all we knew was the acceleration, we could find the area underneath. And we could look at that first rectangle between 0 and 1. That would tell us that after 1 second, we should move 1 times 2 is 2. And then if we looked at that next one, we're going another 2. So we should be up at 4. And then another 2. And then another 2. And then another 2. And again, that area, each step along the way, is giving us those points. That's pretty cool. But let's now take it from this velocity to our position function. So, same idea here. 0, 1, 2, 3, 4, 5, right there. There's our time, and now we're dealing with position on the y-axis right there. And so, if I find the area underneath this graph, let's do it in pink. If I find this area between 0 and 1, that should tell me how far I've gone after 1 second. So that is a triangle. The base is 1, the height is 2. 1 times 2 divided by 2 is 1. So my first point is right there at a y value of 1. My next point should be the area of that full triangle right there. So now the base is 2, the height is 4. 2 times 4 is 8, over 2 is 4. So my second point is right there at a y value of 4. Third point should be this whole triangle right there. Now my height is 6, my base is 3, so I'm going to get 9 as that triangle. Not triangle, well, yeah, sure, area of that triangle, why not? And then my next one is going to give me a total area of 16. So now I'm up here, and then my next one is going to give me a total area of 25. And if you realize what's happening here, all of these points are corresponding. That's a terrible x squared graph, but all of these points are corresponding to what we found by finding the indefinite integral. They're all corresponding to that graph t squared, and it makes sense. If you integrate a constant function, you get a linear function. If you integrate a linear function, you get a quadratic function. Same thing in the other direction. Take the derivative of a quadratic, you get a linear. Take the derivative of a linear, you get a constant. Crazy. So, huge idea. When you're finding a definite integral between two x values, you are finding the area between the graph and the x-axis. That is nuts. So here's a little image to help you visualize that. This should be read as the definite integral of f of x from a to b is that blue area underneath that graph. And so, if we know some basic geometric areas like a rectangle, base times height, or a triangle, base times height divided by 2, or a trapezoid, average of the bases times the height, or a circle, pi r squared, well, if we know some basic formulas, we can calculate tons of areas. So if I have some piecewise function like this, I can calculate all of these integrals pretty quickly. So the first one is saying the integral from -10 to -5 of this function f of x is what? Well, that's just asking for the area of this pink rectangle right there. And that pink rectangle has a base of 5 and a height of 3, so it's an area of 15. And the integral from -5 to -2 of f of x is just the area of this green triangle right there. And that triangle has a height of 3 and a base of 3, so it has an area of 9/2, or 4.5, if you will. C, -2 to 6, is telling me it wants the area of this semicircle right there. Well, semicircle is pi r squared over 2. The radius, if I'm going looking at that diameter, -2 to 6 is 8, so the radius is 4. So I'm going pi 4 squared is 16, but I'm dividing it by 2, so I get 8 pi. And then finally, from 6 to 10, this area right there is a triangle. It's got a height of 2 and a base of 4 from 6 to 10 right there. So that area is going to be 4 with the stipulation that it is negative because that area is below the x-axis. And then if we want to find that total area, just add everything up, all the positive and negative. So pink plus green is going to give us 19.5, and then minus 4 is going to bring us back down to 15.5. So this total area is going to be 15.5 plus 8 pi, which you could approximate if you wanted to, but let's just leave it, as a exact value like that. I'd probably write this though 15.5. That's kind of ugly, so I would instead write this as 31 plus 16 pi over 2. Haha, whatever. So one last problem here. We have some function f of x. We don't know what it looks like, we don't know what the equation is, but we do know these following definite integrals. We know, might help you to draw here, we know that from 3 to 5, the positive area is 20. But we also know that from 3 to 9, we know that that total area there is 30, which means from 5, integral from 5 to 9, that green area right there has to be 10. 30 minus that 20, so we know that integral is 10. And we know from 9 to 10, the integral is -5. And so, if we want to know the integral from 5 to 10, we're looking from there to there. So we've got that positive green, which is 10, 5 to 9, and then we have that -5, that black there, so a total area of 10 minus 5 gives us 5 as our answer.